So let me thank Dr. Vivek Laha for
Thank you, sir.
sharing the two paper presentations. And certainly, since we are running little late, and the keynote talk is much more important as
Yes,
well
yes.
than paper presentation that can be done in other parallel session. So I'm really thankful to Professor Khamsi, who has accepted our invitation again to continue his talk. The remaining part he will finish and he will deliver here. And one of us are actually interested to listen to him. So I hand over this chair to Professor Sahu to chair the talk keynote speech of Professor Khamsi. Please, Professor Sahu.
Thank you, Professor Som. And really, it is a nice opportunity to hear again to Professor Khamsi for his nice talk. And we hope that audience will get some new and some more ideas from his talk. So without the introduction, now I invite Professor Khamsi for delivering his talk. Professor Khamsi, please.
Hi, everyone. What is Qamar? Qamar is not here. I'm sorry, what is he? Uh-oh, I'm going to send him a nasty email. Okay, so let me continue then on where I stopped yesterday. And Qamar said something earlier that I wanted just to clarify. He clarified this, but the fact that he's dying to go back to face-to-face, and he said at the same time that he was able to give 3 talks this month. He would have never given these 3 talks if it were face-to-face. So yes, there is the social cultural exchange that is the case that happens when we are in face-to-face. If I go to India, there will be a lot of exchanges from a cultural point of view than by doing this online. So there is no doubt about it. There is always something that you are going to pay, and there is some advantages. And I'm sorry to say that it has been a wonderful meeting, 3 days, wonderful 3 days, well organized, with these papers, presentations, and so on and so forth. So you have the youngest, the seniors, etc., etc. Technology is quite helpful in this regard, and I encourage you to continue, even if we go back to face-to-face, to have it hybrid to allow other people from outside to participate. Okay, so let me now share with you. And okay, so here, let me, so where was I yesterday? I wanted to talk a little bit more about variable exponent spaces and the stuff that we are doing, but I got carried with the issue of the origin of matrix spaces and the distance. So remember, same day, 2 days ago, somebody presented a paper or a talk on S distances, S metric spaces. And once he's done, one of the questions was whether there is an example on usefulness of that concept of S metric spaces. Again, it's common and it's natural. That's what I was talking about when I said these generalizations, whether they are worthy or not. And that's what I wanted to show you about vector value distance, and even the concept of a distance that we are still looking for. We don't know. I'm telling you, if I start talking about this subject, it will take me another 2-3 hours. So let me move on to the case of the concept of the modular. Okay, so I left you yesterday where Nakano was able to see something that Orlich did not see. okay? And once Nakano gave a formal definition of these objects, which is the modular, then the school, the Polish school, I'm talking about Paso Polish school with what his name, Orlich and Mushilak, they developed it. There is a book, in fact, on modular vector spaces as well by Mushil, oh, come on. Come on, is here. Man, I was about to send you a nasty email, my friend, a nasty email. Anyway, so keep in mind that the concept of modular, which unfortunately many people do not pay attention to, is a natural extension of what is a norm, okay? And that's what I wanted to present to you, in my first talk. So now, because my talk is about these geometric properties, let me go back and take you to the definition of what is uniform convexity. And I want to apologize because somebody was asking me after I was done about why do we use the word convexity? And they said something, if you go back to recording, that is not correct. I used the word smoothness. But in fact, smoothness is something totally different, okay, in terms of differentiability of the norm, etc., etc. But what I meant is not uniform smoothness. I meant rotound. In other words, what we call uniformly rotound spaces. They use round. You see what I mean? That's what I wanted to say. Some people do not use the word uniform convexity. They use uniformly rotound Banach spaces. So I'm sorry, I said the word smooth, and that's a different concept altogether. And as I said in my talk, by the way, that the dual of a uniformly convex Banach space is uniformly smooth Banach space. But anyway, so it's uniformly rotound Banach space. So here is the definition. And I did explain what it means. It means that the middle point is inside the sphere, but is inside the sphere in a uniformly fashion, okay? As long as X and Y are far apart with a control over the distance between the two of them, then the middle point is inside, away from the sphere. Okay. And this concept goes back to 1936 by Clarkson. Okay, he's the one who gave this formal definition. And the only example for Clarkson was Hilbert, capital LP and small LP. Okay, these are the examples because of the inequalities I told you about. This inequality is just because it's simple for P bigger than 2, and it's really beautiful. And if you go back to, I was talking to Kamar this morning about manifold Hadamard manifolds with the negative curvatures. They have some inequality like this with P equals 2, of course, where it becomes like a characterization of this Hadamard manifolds with negative curvatures, cut zero spaces. Okay, anyway, so it's a beautiful inequality, okay? And it allows us to show in a very simple manner, because of the control over this one, okay, that we have uniform convexity, uniform convexity. I want you to pay attention to the definition here. What do we have here? We have norm of X minus Y bigger than epsilon, okay? And here, what's going to happen to us? We're going to have norm of X minus Y. It will involve this term, but the 2 will come out, yeah? The 2 to the power P will come out. And that's why you have epsilon to the power P over 2 to the power P, okay? But keep in mind, once I make P a variable, the exponent variable, the 2 to the power P, if P goes to infinity, this term will go to 0. And then we are in trouble. And that's why when the P's, when they change, in the variable exponent case, when they change and it goes to infinity, you're in trouble. Definitely you're in trouble, okay? So I want just to show you this to keep it in mind, okay? So remember, if the 2 stays inside, we are safe. If I have A minus B over 2, so a norm of X minus Y over 2, we're safe. The problem is the people did not see all this business because we have homogeneity and they don't have a problem. Okay, so if you remember, these are the Orlich spaces, okay? That was Orlich 1932, and basically just changed what? the t to the power p function by a similar function, okay? A similar function. The problem here is what? The norm now is complicated. And he saw it, by the way, from the beginning. I'm talking about Orlich. The norm, he did not, it wasn't called Luxembourg norm at that time, in 1932, 33. But the norm, as you can see there, it's defined using the integral, but in a it's what we call the Minkowski functional. Do you understand? If you take the integral from 0 to 1 phi of less or equal than 1, that's a convex, that is symmetric and absorbing, etc., etc. It has all the assumptions to define the norm via the Minkowski functional, okay? Minkowski functional. And that's what you see there, basically. Huh? But it's defined in an indirect way. That's why what are the conditions on phi that will give us a uniformly convex Banach space? Uniformly convex Banach space is extremely complicated, okay? The case is extremely complicated. Or under what assumptions the space is reflexive? Extremely complicated. All these assumptions are complicated compared to the case of capital LP and small LP. Of course, you do have, in a similar fashion, the little l phi, the Orlich sequential vector space. Okay, so now, so that's what I said. The little l phi is defined in a similar manner with the norm similar to that. Now, what happened when you want uniform convexity? If you want uniform convexity, your function phi must be nice, not just convex. No. Must be very nice. And they call it, for the people working in the area, very convex function. Okay? Very convex. There is a precise definition. Huh? So phi has to be very convex, but it needs to have delta 2 property. In this case, the norm is uniformly convex and the modular is uniformly convex. Okay? So here, let me give you an example where delta 2 fails. Okay, is the two examples that you see there. Okay, and these examples, delta 2 fails because if you take phi 2 to t, you're going to have exponential of 2t squared. For example, here, if you divide by phi 2t, you will go to infinity. You will never be upper bounded. Okay, but they are very convex. Do you understand? So they are very convex, but they are not satisfying the delta 2 property, and therefore the spaces associated to them, the norm is not uniformly convex. Is not uniformly convex. So these cases, these examples, they escaped the Polish school. They did escape the Polish school. So when I met, well, I'll show it to you in a second. So here we have the definition I told you about Nakano, who saw this object. I'm talking about the modular, okay, and the concept that you have right here with the assumptions, okay. And as I told you, what are the assumptions that are failing us is the triangular inequality that we don't have, as well as the homogeneity that we don't have. These two are terrible. Okay, so you have to work, like, for example, you will be amazed when we talk about modular Cauchy and modular convergence, which I will show you. In other words, a modular topology that was defined, by the way, by Nakano. He knew about this, huh? In a similar fashion that you have the norm coming at the distance and the topology generated by the distance and by the norm. If you look at the modular, we have a similar approach to define a topology from the modular. Okay, but you see, because you don't have the triangle inequality, you cannot now compare Cauchy with convergence like we do in the case of what? In the case of the distance, because of the triangle inequality. Number one. Number two, you have to be careful about uniqueness of the limit. Okay, so all this is quite tricky. Then you're like walking on X. You have to be careful. Basically, you have to be careful. Okay, some stuff are true, like the uniqueness, for example, of the limit. But what I'm trying to say is that you have to be careful because you don't have the triangle inequality. Okay, now the modular on a vector space, according to Nakano, you have a vector space, a modular vector space X row, and on that X row you have a norm. Okay, so you do have, of course, a vector space X. Row is defined on X, but the norm is defined on X row, okay? And not necessarily, by the way, complete, not necessarily complete, okay? So you need to have delta 2. If you have delta 2, it makes your life lot easier. And there are variant definitions of delta 2, okay? This is for the modular, of course. And now Nakano gave this definition. Slightly different with R, okay? He took R equal 1. He was mimicking what? The original definition I gave you about the uniform convexity. Anyway, it's not really a big deal, to be honest with you. Quickly, you can see that the R is necessary and you cannot miss it. So you have this definition of modular uniform convexity, which mimic the case of the norm, okay? To the best of my understanding, I mean, I don't want to tell you what was in Nakano's mind. This definition is bad, okay? Why? Because you cannot trust the norm. You see, if you are going to work with concept that's coming from the norm or from a distance, and you want to do them for some abstract structures, you have to be careful about this, okay? Because sometimes there are things that can, play tricks on you. So, for example, here, the rho of x minus y is coming from the norm of x minus y. But in all concrete examples, it's not the norm of x minus y that shows up. It's the norm of x minus y over 2. But because of the homogeneity of the norm, then it disappears. We don't see it. Okay? So anyway, so he gave this definition. Okay? And here we have some, of course, beautiful results, especially the LPN, the variable exponent sequence spaces, that he did, by the way, himself. But anyway, so let's continue. This is what I was explaining to you. If you look at the inequality I showed you at the beginning, if I want to write it for phi of t equals t to the power p, it becomes like this, the way you see it, guys, okay? And as you can see, the 2 is inside. So now, of course, it gives us this now, okay? But because the rho of 1/2 x minus y will not give us 1/2 rho of x minus y, so we have to keep the 1/2 inside. And that is exactly the point I shared with Kozlovsky and Chen Shutao. You see it? So here, this idea, this simple idea, was amazing. And I will show you now in a second why. And this is exactly what I was talking to Chen Shutao and Kozlovsky Wojtek in that 1988. We met in 1988. Paper appeared in 1991. It was in 1988 that we saw this. And again, as I told you, if you're looking for this guy, his name is Shutao Chen, C-H-E-N. But I'm still puzzled why we didn't see it. So you see, we came up with a new definition, and now we have rho of x minus y over 2. Okay, so it's slightly different from the one that Nakano gave. Okay, good. So now we called it UC2 because of the 2 that you see there. Okay, fine. So now what happened? If you are UC, then you are UC2. Why? Because rho is convex, and the rho of 1/2 x minus y is going to be less or equal than 1/2 rho of x minus y. Okay, so rho of x minus y will be bigger than 2 times r epsilon. I'm talking about here. You see, rho of x minus y will be bigger than 2 times epsilon times r. Okay, so that's why you have this inequality here between the 2 of them. If this one is positive, this one will be positive. So if you are uniformly convex in the sense of Nakano, okay, you are uniformly convex in this new sense. Okay, so what happens if you take delta 2? When you take delta 2 off, then the converse may not be true. The converse may not be true, okay? You may be UC2, but you may not be UC. Okay, if you have delta 2, then the answer is yes. Yeah, they are equivalent. And that's why here we have the example exponential t squared minus 1, and we show that in this paper with Chen Shutao and Wojtek that we do have UC2, but we don't have UC. That is the point. So we were able to catch a new class when delta 2 fails. Now, I will say something later on. Why is that important? So someone will ask, okay, fine, but what is it exactly? So let me give you now the topology I was telling you about. This is just the modular topology that you can find back to our friend Nakano, okay? And what I wanted to pay attention is the last one. okay, which is the modular diameter of a set, the modular diameter of a set, okay? And you can also define the distance of a point to a set as being the infimum of rho of, okay? And the reason is because of the talk that my friend Kamar was talking about. It has some implication, and I will show it to you right now. Now, once you have UC2, what happened? Okay, do we have some behavior? Because remember, people do not know UC2. Okay, because if you don't have delta 2, you don't have uniformly convex. Okay, in the case I just showed you with exponential t squared minus 1, and therefore the people do not touch the structure of the space. But now what happened if the space has UC2? This they did not know. Okay, fine. Okay, you have UC2. So what? In other words, you don't have uniform convexity, the modular uniform convexity, but you have the modular convexity UC2. So what? What kind of behavior do you have? Look at now number 1. It says what? That if you have C, which is non-empty row closed convex subset of X row, let's take X such that the distance from X to C, the modular distance from X to C is finite, or if C is bounded, for example. Anyway, so you have a unique projection. Do you see it? The infimum is rich, and you have 1 point. The uniqueness. This is unheard of if you are looking at in the absence of uniform convexity. Okay, great. So in other words, C is row proximal. Okay, and now look at this property. This property is important. What does it say? Property R. What does it say? It says that basically you have some kind of weak compactness. Okay, weak compactness defined by the family of convex sets and their intersection. So, for example, if you look at the case of that he was talking about, our friend Kamar, if you have a little bit more on the, and you take the convex sets as being what, as he defined, whenever you have 2 x and y, the geodesic is there, okay, in the set, then you have this kind of weak convexity. It's not like normal convexity. Okay, it's not the linear convexity. This is one way to look at convexity. There are other ways, like what a French mathematician did, and we used it a lot. But in any case, here, what do we have? This definition that you see there of row closed convex non-empty subset decreasing, okay, I think decreasing sequence. If you go into the norm and you take closed for the norm, you end up having a reflexive Banach spaces. It's a small linear result of reflexivity by an intersection property on the convex sets, okay? And that's why I called it property R. R comes from reflexivity in a very old paper where Malutab showed that if you have uniform normal structure property, you are reflexive, okay? And I wanted to show that result in metric spaces. Why? Because uniform normal structure property is a metric property, okay? And I wanted to show that we have this property R. I couldn't call it reflexivity. She showed reflexivity. Okay, she used the linear characterization of reflexivity. Here, I'm using this intersection property that gives me what? The property R. And it's very interesting because it has many applications, this intersection property. It's like compactness, by the way. Okay, good. Now I want to talk about variable exponent spaces. And someone may ask, how useful are these variable exponent spaces? Why do we have to study these variable exponent spaces? If you want to know about variable exponent spaces, this is the book, okay? This is a fundamental book that you can find everywhere on the web. I have the e-copy, and this is the book that if you want to learn about this business. Of course, here is mostly about PDEs, okay? And integral equations, et cetera, et cetera. And because the vectors they deal with are functions, so basically they're looking at capital LP of omega. In other words, they are not looking at the sequential case. They are not looking too much on the sequential case, okay? But this is the book, if somebody is interested to learn more about this. Now, why this is becoming the area? And you have to go back because you look at the dates, 1947, 1949, but in fact, the boom started after 2003. Okay, that's where the boom started. Okay, so you have this liquid, okay, that people were using in the brakes. What is special about these smart fluids or electrological fluids, ER fluids, is that especially look at the giant electrological fluid. These ones that were discovered in 2003 by the American Army is what it does, in fact, is a liquid that moves in a fraction of a second under the impulse of an electrical shock that's going to go into the order of milliseconds, okay? Milliseconds, huh? And the structure of that liquid goes from jelly to something hard, extremely hard, okay? And this was a motivation to a series of, in fact, it was a movie, and then to a series from an idea of Einstein, and I wanted to show it to you. Let me show you. This is what's known as Stargate. Okay, and as you can see, it uses these passages of Einstein to move from one universe to another one, from one planet to another one. Okay, and the liquid that you see there, it's a jelly shape. It's in a jelly shape. The people, your soldiers, that's what you will see if you watch the movie or the show. The soldiers are coming in, okay, and they will walk in, and the moment they walk in, they hit a key that will send an electrical shot to the Stargate, and the liquid becomes a solid, but beyond solid. I'm not talking about solid. So the aliens will not cross and will not go, because no arms, no nothing. So you can see that the army or the military are interested into this. Okay, now what is it about these smart fluids? When you try to model them, look at the authors, by the way. So Ruzicka is one of the authors. He did a lot of work on this. He's one of the authors of the book I showed you. Look at the equation there, where this Laplacian equation is an eigenvalue problem associated with Laplacian, is with a p of x that is variable. Okay, and if you look at the weaker form associated to this equation, it will give you this integral equation that you see there, where lambda is a constant, but now p of x is variable. So you see now what we have is an integral with something to an exponent, that the exponent is changing, okay? So the exponent is not a constant, okay? Now, there is, within the theory of variable exponent spaces, there is, oh, I forgot to mention something here. Look at here, because you have the divergence here, so you have a derivative. That's why you need Sobolev spaces, okay, with variable exponent. That's the idea behind Sobolev spaces. So now let's look at this problem. It's known as the Dirichlet energy integral, okay? That's what you see there. And the problem, again, look at the power, the exponent, which is variable, okay? The exponent, which is variable. So you cannot treat this problem, which is finding the infimum of, you see, the problem is to find a minimizer of the energy. So you're looking at the infimum of the energy, okay? And what you have there is a problem that you cannot solve. You cannot solve by looking at the constant case and helping you. You cannot, okay? But I want to show you something here, because I talked about it with some of my friends, and we're still looking into this problem with a friend of mine who worked a lot on this. Hamar knows him very well, Osvaldo Mendez. And what I wanted to look at here is that this is like the modular, okay? The modular of the gradient of u of x, yeah? And we're looking at the infimum of the modular. And basically, what you're looking for is the distance, the modular distance of 0 to a certain set. Okay, that's what it is, because you are looking at the infimum for certain function u such that, okay? So here, what we want is to be able to say, like the problem I showed you with UC2, that you have an infimum and its unit, which is the distance from 0 to that set. This point here, still not used, and I didn't have time to go to it, to be honest with you. Okay, so here is the example again. LP, I talked about it last time. So we have this space which was extensively studied by Nakano, and of course in 1971 by Sundari-san and Waterman Bauer. They looked at the structure and some of the properties of this little LP, okay? Like when do we have reflexivity? When do we have uniform convexity? According to Nakano, according to Nakano, in the definition that he gave. So both Sundari-san and Nakano, they found that you have that kind of uniform convexity if these two numbers are away from 1 and infinity, okay? So that's what you see here. This was known to Sundari-san as well as our friend Nakano, okay? Okay, now where am I? Now let's go here and let's look now the case where delta 2 is not there, which means that P plus, in the case of little LP, I'll be only talking about little LP, but believe me, we have similar conclusion for capital LP, okay? We do have it. Well, let me just explain to you what happened with little LP, okay? So when do we have, let me take you back. When do we have that delta 2 fails? When? Well, so let's look at rho. Rho is going to be this one without the lambda. Rho of xn is this one that you see here. If you take rho of 2x, you are going to have 2 to the power what? P of n. So if P of n is unbounded, the rho of 2x may become infinite, even if rho of x is finite. In fact, we can show that you don't have delta 2 if and only if the P plus, you see it, is infinite. So when P plus is infinity, then everything goes bad, okay? So that was the first thing we did. We looked at the case where P plus can be equal to infinity, but P minus is away from 1. So remember, P plus can be equal to infinity. Therefore, we don't have delta 2, okay? But P minus is bigger than 1. Okay, so here, what do we have? So here we show, if you have this, look what happened. You have these convex, which are proximal. Okay, that's what I was telling you. In other words, you have that infimum. And you have property R. This is interesting. So this people did not see, because if you look at here in this paper by Waterman, Barber, and Ratti, you do have this kind of reflexivity and summability when P plus is finite. So when P plus is finite, the two topologies, the norm from the Luxembourg topology and the modular topology, they coincide. Okay, and then of course, if you have the delta 2, if you have reflexivity, then you have this property R I told you about, because I'm saying R for modular convex sets, modular closed, but in fact they become non-closed if you have delta 2. So they are all connected. So when delta 2 fails, we're in trouble. We really are in trouble. Okay, so here now let me show you what happened when the infimum of P of n equals to 1. So now here, the infimum bigger than 1. Then we have these properties, and of course we do have the fixed point property. I'm talking about Kirch's fixed point theorem, etc., etc. So I didn't show you all this, but we have all the theory that we started to build. Okay, but what happened when P minus is equal to 1? When P minus is equal to 1, then it depends equal to 1 what? What do we mean by equal to 1? So it's something I worked on with Osvaldo. And look at this. This is a definition that was introduced by Garkavi. It's called uniform convexity in certain direction, or in every direction. Okay? It's just definition is weaker than uniform convexity, the normal uniform convexity, okay? Just for the sake of, guys, the first paper I read in my mathematical career was a paper by Zisler, who worked on renorming spaces to make them uniformly convex in every direction. Yeah, and this uniform convexity in every direction implies the normal structure property, which in turn implies the fixed point property for non-expansive mapping. So just to show you that the background is very helpful to know, okay? So here it is. So as I told you, this is a concept that was introduced by Garkavi, okay? And now we have this. So we have strict convexity, we have uniform convexity in every direction, and we have uniform convexity. That's it, okay? So here, what happened when the infimum of P of n is equal to 1? We looked at this case. Then look now this property. This property, if you are asking what is A and O, that's Amin and Osvaldo, okay? And we looked at the case when P of n is equal to 1. We allowed 1 to be equal to 1. We allowed 1 P of n to be equal to 1. So we say here, the condition holds if you have at most 1 element. So only 1 P is equal to 1. If you have 2, then you have R2 with the norm 1 and everything fails, okay? But if you have only 1, okay, which means you have R, okay, with the absolute value, okay? Inside, of course, inside. So here, so if you have this condition, so P minus is equal to 1, you can make it equal to 1. Look at the PNs, they go down to 1, then the infimum is 1. And you can even allow one of them to be equal to 1. Therefore, the infimum is equal to 1. Okay? So remember, as I told you before, P minus equal to 1, P minus equal to 1, P plus equal to infinity, P minus equal to 1, P plus equal to infinity. People did not touch this. They really took their hands off. They worked only in that book I showed you about variable exponent spaces. They only work with P minus bigger than 1, away from 1, and P plus away from plus infinity because of some embeddings and so on and so forth. Okay? But the other case, the people were completely, so when Osvaldo went to a conference on variable exponent spaces and he started talking about this, everybody was shocked because they never thought that something good can happen in these extreme cases, Okay, so here we are. So if P satisfies the AO property, then we are uniformly convex in every direction, and we are strictly convex. Let me just say something, that the uniform convexity in every direction implies strict convexity in the modular sense as well as in the norm, well known. So that's not a problem. And if you fail, if you have more than 2 elements equal to 1, then you have little L1 R2 with the norm 1. And that's it. Both of them fails. You are not, because remember, the unit ball of little L1 R2 with the norm 1 is not strictly convex, okay? So here, what happened in this case, when you have this AO property or AO condition, then everything is equivalent. That's amazing. In other words, strict convexity and uniform convexity in every direction are equivalent. That's amazing. Yeah, that is truly amazing. Okay? Okay, so now let's go here. What happened? Let's see B a non-empty row closed row convex bounded convex subset of LP. Assume that C satisfies the property R and this K be a non-empty convex subset, then K is row proximal. Okay? For any X in C, if you look at the set that Khamar was talking about earlier today, this set here, okay, that will give me the distance is not empty, okay? Good. But if your row is strictly convex, then this set is a singleton. It's not multivariate, it's just a singleton, okay? So you have only one point, what we call, in this case, we say it's a Chebyshev subset, and P, the projection of X is a singleton there, okay? But in general, it's okay. So now, if you have property R and row is strictly convex, what happened is this intersection that we had for a sequence, you don't have it only for a sequence, but you have now for any family, okay? Yeah, for any family of convex sets that are, of course, directed downward. Directed downward. Be very careful about this. If this holds, you see where I'm going here. If you have strict convexity and you have a map that is non-expansive in the modular sense, the set of fixed point will be convex, row closed. Okay, convex, row closed. If the domain is bounded or row bounded, then the fixed point set will be row bounded. And if you have this property, okay, property 2, then you can show that any commutative family of non-expansive mapping, they have a common fixed point. And how do I show that they have a common fixed point? By looking at an intersection of their fixed point sets. You see now the idea? So this result is really has some major implications. Some major implications. Okay, so here, where are we now? So here, assume C has property R and rho is uniform convex in every direction. It's going to be, of course, strictly convex. Then you have this result. No, I'm sorry. Here is given in terms of a modular. So I'm giving you these properties are valid in a modular vector spaces, okay? And now, what I was talking about, let's take T from a set C to C, and we say that it's rho non-expansive if you satisfy this. Here, if you're reading about this business in the literature, you will find out that some people, they start to put numbers here and here inside rho, okay? Good. And what happens when you put these numbers, you end up having the non-expansive behavior for the norm. You see now? So if you throw a number here, some numbers here, they do it so the map T will be non-expansive with respect to the Luxembourg norm, or a contraction with respect to the Luxembourg norm, so they can use the classical Banach contraction principle or the classical fixed point theorems for non-expansive mappings, okay? But here with Kozlowski in 1988, with Shimon and Kozlowski, we initiated this area where we wanted to look at something that's easy to verify on the integral. Because remember, if you look at the module in the case of ordered spaces, but also in modular function spaces, rho is defined by an integral. So I can check if my map T is simple, is non-expansive with respect to that integral. Okay, and with Mustafa Bashar, we looked at some integral equations where again it's easier to work with what? With the integral than to work with the norms, because they are very defined in an indirect way. Okay, so where am I now? So here we have the infimum of P of n bigger than 1. The infimum of P of n bigger than 1. And if you remember, then what do we have? We have property R, we have the uniform convexity UC2. I'm talking about LPN here. So you have everything is there. And now you have this condition that assume that I'm talking about if we don't have the infimum of P of n bigger than 1. If P minus is equal to 1, we allow P minus to be equal to 1 now. We have the Kirk fixed point theorem and all this stuff from UC2. But what happened when the infimum is equal to 1? Okay, that's what I meant. Does not require that infimum P minus equal to bigger than 1. So what happened when P minus is bigger than is equal to 1? In this case, we need AO. So we allow only one P of n to be equal to 1 at most. Okay, at most. So remember, the infimum can be equal to 1, but they are all bigger than 1. I mean, like 1 plus 1 over n, for example. If I take P of n equal 1 plus 1 over n, they will all be bigger than 1, but the limit is equal to 1, and therefore the infimum is equal to 1. Okay? So the AO condition will be satisfied because there is no n for which P of n is equal to 1. Anyway, so if we have the conditions AO, we have the uniform convexity in the modular sense in every direction, okay? And now we are able to show what? Kirk fixed point theorem, because we have property R, okay? And we have the normal structure in the modular sense, and we can show that any rho non-expansive mapping, you have a fixed point, okay? Good. And as I told you, because of that idea that it's any family, the intersection, the property R can be extended not only to a sequence of convex sets, but to a family of convex sets, okay? Then you have here, this result can be extended to a common fixed point for a commutative family, yeah? For a commutative family. So now, what happened to capital LP? All the results I showed you, are in fact extended to capital LP, okay? It's slightly different. For example, okay, what does it mean? AO, the condition AO. At most one n such that P of n is equal to 1. What do you mean? You understand? So the condition becomes, in this case, just to show you, in the case of capital LP, the condition become, you look at the set where P of n equal to 1. P of n equal to 1. And what you want the measure of this set to be equal to 0. Yep. See, that's the condition. Our condition AO becomes, in the case of LP, capital LP of omega, that the measure of the set where P of x equal to 1, okay? So I said P of n, sorry, I'm no longer sequential, I'm talking about functioning, P of x. So the set where P of x is equal to 1 has measure 0, okay? And we are able to prove the same results, the same theorem. Thank you very much, everyone. It was really amazing and enjoyable. And I still have time if you have any question for me.
Yeah, Salim, Amin.
Yes, sir.
Please.
I have two questions.
Go ahead.
Okay, the first question is you have presented the fixed point theorem is similar to the what is the name? This fixed point theorem for non-expansive map. The
Correct.
last theorem. Okay, Kirk fixed point theorem. Do you have any iterative schemes in case of modular convex functions like Man or Ishikawa or any method to find the fixed point?
Do I have to answer?
Yes. Then I will ask you the second question.
Oh my goodness. You are terrible, Khamar. You are terrible. Okay, I'll answer you. We did not touch it, yeah. So the question is not that it's open, but we did not touch it. We are, as I said in my talk, on if you remember, in my original talk, what did I say? I say this is just the top of the iceberg, okay? Or if you want, the tree that hides the forest. That's what I said, okay?
Yeah.
So more about these variable exponent spaces is to be discovered. But again, what is the idea I'm trying to convey to all of the people right now in this conference, especially the students, whether they are going for their master's or their PhD. The idea is don't always focus on the norm. This is the idea. In other words, focus on the modular, okay? As Nakano did, okay? And if you look at, for example, the book I showed you, let me go back there, okay? Let me show you. I want to show you.
So you mean that it is an area where the young people can do some work?
Oh, beautiful. Definitely.
Yeah. So it is the young people can see.
Yeah. See here, if you look at this book, which is crucial, it's a very vital book to all the people in Europe who are working in the school, who are working in these variable exponent spaces. You will see that the modular is crucial, central as a tool to work with. Okay, the modular. So what I'm trying to convey here to the people is that you have to understand that if you stick to the norm, because it's an extension of the distance in the vector spaces, the norm, but you limit yourself. If you are working with the modular, you open up your mathematical range and views and so on and so forth. That's the idea I want to convey here. That's exactly the idea I want to convey here.
Okay, now my second question is, then I will say thank you.
By the way, come on, is my room ready? Is my room ready?
Okay, okay. My second question is,
Kamar, he built the house and he made a special room for me. Yes or no?
yes, yes, yes. I am at home. You are most welcome. You are most welcome. We will be very happy to see you here.
Thank you.
Yes. My second question is, you see, you remember before last year when we had a workshop on fixed point theory in KFEPM, there was a Chinese guy from King Abdullah University of Science and Technology, and he presented a boundary value problem for fractional order. Okay, here you have variable order. And then what he did, he used the same technique as used by the other people for general Sobolev spaces. And then by using something, he converted the problem into the variational problem. As in the morning, you see Professor Akhtar mentioned that the problem can be written in the variational form. And then he used the Dirichlet method to solve that problem. Is it possible here in this case? Because you showed one boundary value problem for the variable ordering. So is it possible to write this boundary value problem in the form of a variational problem?
Okay, so let me first, your question has two things into the same question, okay? Let me go to the first case. The first case is this, this issue of fractional calculus, okay? What Qabbaj, that you know very well, says, he calls it the new religion, okay? And I sat down because one of my colleagues here is an expert, Professor Kiran, and he's an expert on fractional calculus. And I did ask him this specific question. What is exactly something that we advanced with fractional calculus? Forget about the publications, forget about the journals, forget about the publications. My question is there something that we couldn't handle in the traditional calculus that fractional calculus was able to give us a deeper understanding? And the answer was, as you will be shocked, none. So we have this fractional derivative as a definition and what we can do with it, but we don't have any something important. In the case of variable exponent spaces, there was a motivation, especially these smart fluids. Okay, in 2003, the people, they started to study them because many of the PDEs, they involve that P relation with P variable. And it's a beautiful book, by the way. So my point is, there is a motivation, concrete motivation for variable exponent spaces. Now, the people, what they did from 2003 all the way to 2020 till 2021 is to look at differential equations and PDEs into these Sobolev spaces, but with P minus bigger than 1 and P plus less than infinity. Okay, great. So now here Amin comes in, okay, and they start to look at P minus equal to 1, P plus equal infinity. But wait a minute, I only gave them example of Kirk's fixed point theorem. Why? Just to show them that there is something beautiful in the extreme cases. But wait, what about variational problem? What about the case of, as you said, all this iteration? So once we start looking into all this, then it becomes richer and richer. We are telling them what happened in the cases that you guys eliminated because you said they cannot work there. So if we go there, so this is just opening the door, and I'm hoping that students, especially students who can look into this case, it's a beautiful case with some good motivations. That's the idea.
Yeah. Okay, thank you very much.
You're welcome, Khamar.
Now, thank you.
Any more comments
Okay.
from audience?
Don't be shy. Don't be shy, huh?
For the youngster, I must say that, and some youngsters can jump in this area. It is a very nice area to
This is
work.
the right platform. At this
Yeah.
moment, you can ask some questions if you are having. So it's really a wonderful talk of Professor Khamsi. But I have also not any comments, but I also see the some new kind of the window from your talk. The first point, the condition AO is very strong assumption, because the condition AO has some equivalent structures with some 4 condition. So I don't think that there will be the replacement of the removal of the AO condition. Second one, there is a geometric structure of the space, and due to that one, we can discuss, we can investigate the behavior of the metric projection operator, because you are getting the best approximation, and the best approximation is unique. So the continuity and some other things can be also studied here. And next, you are having the norm phenomena. That's why on the basis of the norm phenomena, we can get a new differentiability, because it is not enjoying the exactly uniform continuity, but you have a nice property, the UC2 property. So the for whole theory, UC2 property has nice role. So these are the many more points, and I really enjoyed the whole the lecture. Thank you very much, Professor Khamsi.
Yeah. Thank you. You're welcome. You are welcome, Karjin.
Sir, you have talked about modular vector spaces. And there are many results on modular spaces and then integrals. So is there any connection with that vector space with modular space? What are the connections?
Okay. Again, remember, what is the reference? If you can have it, of course. Okay. What is the reference? I think I gave it last time. Oh, here. So this reference here is about modular vector spaces. Okay, modular vector spaces. In other words, you take a vector space and you put a modular on it. Okay. So remember, what is the novelty of Banach? Okay. Before Banach, before 1922. Okay, they were working on vector spaces with a norm, but the norm was defined on a function space. All the examples, they were function spaces or Rn, the classical Euclidean space. Okay, but the concrete interesting examples were function spaces. What Banach did, he told them, no. Let's define the object of a norm on vector spaces. And he called it B spaces. He didn't call them Banach spaces, B spaces or class B. Okay, and he talked about, by the way, completeness, Cauchy, and all this stuff. Okay, so here that is the approach that Nakano did. He saw the work of our friend Orlich, and he defined the modular, and he defined it on a vector space. So in this case, the vectors are just vectors, abstract vectors. They can be functions, and they don't have to be functions. Now, if you want to look at modular function spaces, so let me show you something. I want to show you something. Sorry about.
Hello.
I did not know that somebody will ask me this question, so that's why I didn't open it ahead of time. But let me show you. I want to show you something here. So here, Amin's books, okay, and let me show you. Sorry, this book. Okay, so if you look at this book here, okay, so in this one we are looking at modular function spaces. Modular function spaces. Of course, this book was written prior to my research on variable exponent spaces. I met variable exponent spaces in 2017. Okay, that's where I met them. But here you can learn a lot on modular function spaces. Okay, modular function spaces. So, but again, I'll be honest with you. I would like the people to focus on variable exponent spaces. Why? Because there is a beautiful motivation. That's what I meant. Okay. So if somebody is asking them, why are you doing this? Like the gentleman who did the S metric spaces, and somebody was asking him, give us some usefulness of the S distance. Okay. So it's a terrible question to ask somebody who's doing work and then he cannot answer you because he doesn't know why it's useful. But in the case of variable exponent spaces, there is a usefulness. There is really a usefulness. Okay, so that's why I'm encouraging them. But they can also, of course, work with a lot of stuff. This is now something that we took. It started in 1988, and we took it too far. The origin is a paper that was published in 1988 with Shimon and Kozlovsky. And of course, now we know a lot on these modular function spaces, a lot. But the case of variable exponent spaces, and again, going back to Qamar, things are just scratching the surface. Yeah.
So let me thank both the speaker and the chairperson, Professor Sahu and Professor Khamsi, for his very illuminative and beautiful talk.
Yeah,
This is the last talk of this
Thank you.
series. We are going to have our valedictory session now, and everybody is invited